Hello class. Today we're going to be talking about isomers. We briefly talked about them beforehand when I introduced organic molecules. I gave it as kind of a reason as to why we need to have different naming systems for different molecules with the same molecular formula. Now, this was the example we explored. We explored butane, and then we explored the isomer here of butane, 2-methylpropane. Now, this is just one type of isomer. It turns out that there's actually many types of isomers, and that's what we're going to learn about today. So, first up is conformational. All particles, unless they're at absolute zero, are in constant random motion. Now, molecules about a single bond can actually freely rotate, right? They can freely rotate if there is a single covalent bond. Because of this, these molecules can take up different conformations, right? They can look slightly differently depending on how these bonds are rotated, right? This is one conformation, but if I rotate this single carbon bond here, carbon-carbon bond, this is a different conformation. Now, this is a less likely conformation due to the fact now that we have electron density kind of closer together here, right? This is a much more energetically favorable conformation, but there's no saying that it would not form this conformation at points because it is randomly moving around. Now, keep in mind, these types of isomers, conformational isomers, they are the exact same molecule. This is just rotation around a bond, right? So all their properties are the same, everything's the same. It's just that the bonds can be in slightly different orientations depending on how they have rotated. So for example here, if you look at these butane molecules, they look different, but if you look at the bonding structure of all these butane molecules, you'll see that, in fact, they are exactly the same, right? Same molecular formula and same structural formula. So that's how you know it's a conformational isomer. Molecular formula is the same, structural formula is the same. That is a conformational isomer. Now, let's say, for example, the molecular formula is the same, but the structural formula is different. In those situations, what you have is a structural isomer. Okay, so how can you identify a structural isomer? Same molecular formula, different bonding orientation, right? Different structures. Here, if you name them, you can tell they are different because they will have different names. This is 2-methylbutane, this is pentane. And if you were to count up the carbons and the hydrogens, you would see that you have the exact same amount, right? They are the same molecular formula, different structural formulas, and thus different names. This is another isomer structural of pentane. So, structural isomers do have different properties, right? Because the carbons are fundamentally bonded differently. And if I wanted to create a structural isomer here with the molecule that I've constructed, keep in mind this is a butane molecule, I can move around and bond differently these carbon atoms. I could move a hydrogen to this one here and add the carbon here. And now, again, we have the exact same number of hydrogens and carbons, but they are bonded together in a slightly different way. This would be 2-methylpropane, right? Whereas what I had before was just plain old butane. So again, You can distinguish them because they will have different names, same molecular formula. When it comes to isomers, the number of them dramatically increases with the number of carbons in your hydrocarbon. So if you look at butane, 4 carbons, how many isomers are there? Well, there's only 2 different isomers. There is 2-methylpropane and there is butane. That is it. When you talk about pentane, there's 3. Hexane, there's 5. The more carbons you add, the more possible variations, and this number will rapidly increase. Now, for example, I want you right now in your booklets to attempt to draw all of the isomers of heptane. So 7 carbons, try to draw all of the isomers of them right now. You will find that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 isomers. Did you get them all? Right? They can be challenging to see all of those isomers. The more carbons you add, the more isomers there will be. Geometric isomers are isomers that are present when you have a double bond. Now, some of you took biology with me. What is the healthiest fat? What is the healthiest fat? Well, the healthiest fat is polyunsaturated fatty acids that contain cis double bonds. What is the unhealthiest fat? Well, that's trans fatty acids. What was that difference between trans and cis? Those are descriptions of geometric isomers. Now, when it comes to a double bond, right, this double bond here makes the molecule much more rigid, right? We cannot rotate like we could about a single bond. So the conformation of the bonds off of these carbons here, the carbons of our double bond, doesn't change. As a result, we can make a statement about their conformation. So this here would be considered a trans double bond because the groups that are attached to these carbons are on opposite sides of the double bond. What does the word cis mean? Well, cis means the same. So where do you think you would find this carbon atom down here if this was a cis double bond? Right, if this is a cis double bond, you would find that the carbon would be up here. Right, so if you notice, this is our double bond here, right? The carbon atoms that are coming off of it are on the same side of our double bond, and this would be a cis conformation. Now, if we look at these 2 molecules here, you can see it represented with structural formulas. This here is cis-2-butene, and this is trans-2-butene. And although they have the same molecular formulas, and they also have the same structural formulas, like I said, since those bonds don't rotate, they have different permanent conformations, right? So this here is trans, this one is cis. Now, by the way, the reason why a cis fatty acid is healthier than a trans fatty acid is because that cis bond, you'll notice here, it kind of introduces a kink into the fatty acid. Now this kink makes it harder for those molecules to stack up and solidify, right? They have a lower freezing point as a result, right? So it's harder for these things to stack and solidify, so they have a lower freezing point as a result, right? So this is your liquid oils, your olive oil, canola oil, things like that, contain polyunsaturated cis bonds. Why are trans fats so unhealthy? Well, trans fats aren't something your body regularly encounters, so we process that bond very, very differently than a cis bond, right? So that different orientation means that our enzymes that would break down those cis double bonds, they either don't work as well, or we have to use a different process to break them down. So these trans bonds are much more unhealthy. They increase your bad cholesterol, all sorts of really nasty things. And you can identify them because they are often solid at room temperature. And you can tell if you look on the back of the package, if it says hydrogenated vegetable oils, those are vegetable oils that have been turned from unsaturated fats to saturated fats. One of the downsides is you always get some partial hydrogenation. Well, I shouldn't say always, most of the time. And you're going to get some of those trans fatty acids. Now, since there is no kink in their orientation, they stack up much more easily, and they are solid at room temperature, just like your saturated fats. So, these are two geometric isomers. Which one is cis? Which one is trans? I think you all got it. This one here is cis, right? Same side of your double bond. This one here is trans, different sides of your double bond. So again, this flip of your double bond does have a big impact at the molecular level, right? Our body treats those fats fundamentally differently. Now on to our last isomer we're going to be talking about, which is optical isomers. So optical isomers are effectively non-superimposable mirror images. If we were to look at these molecules here, yes, they are both exact same molecular formula. However, and you can see that this carbon here, is bonded to the exact same subgroups, exactly the same. But I want you in your mind right now to rotate these molecules. Try to overlap them in your mind. The reality is these are non-superimposable, right? No matter which way you flip those molecules together, they cannot be superimposed. As a result, those are considered optical isomers. Now, optical isomers are also quite important when it comes to your biochemistry. Your body can treat optical isomers very differently depending on the molecule. So again, they look the same, but if you were to try to rotate them and superimpose them on top of one another, it's just not possible. That is all for today, class. Have a wonderful day.